All right, good morning, everyone, and welcome to WCEC's affiliate and partner webinar service. Today's webinar topic is evaporative condenser air pre-cooling and RTU optimization using variable fan and compressor controls. Our speaker for today is Teresa Pistacchini, coordinator for WCEC, and your host of today's webinar. Okay, everyone. Sorry about that. We had some technical difficulties. Let me try and share my screen again. Okay, can everyone see the slide that says thank you to our affiliates and partners? And can you hear me? Great. Thanks, Mark. I will continue then. These webinars are a service provided by WCEC to help inform and guide potential energy efficiency decisions for utility DSM programs and beyond. We at WCEC hope you find these webinars valuable, as they are only offered live to our affiliates and partners who support this research. To help ensure the information in these webinars remains relevant to you, our valued partner, I welcome any and all feedback, including topic recommendations. So please do not hesitate to call me or email me with your ideas to enhance the value of these webinars. I'll be providing a contact slide at the end of this webinar, so you may quickly get in touch with me or our featured speaker. WCEC's latest newsletter for April has just been released. This month's newsletter includes new progress from the Western Cooling Challenge and links to published case studies and progress reports from this research. Also included is an update on the rainwater use for evaporative systems project. WCEC would also like to mention and congratulate graduate student researcher Nasim Tajmand. Nasim was awarded the 2014 ASCE Sacramento Improvement Energy Project Award for her work on the rainwater project. If you have a question regarding today's presentation, you may ask it directly in the chat panel, or if you'd like to speak to the presenter and the audience, you can request to be unmuted from the same chat panel. I'll be monitoring the questions panel and we'll ask them to our presenter in the order they appeared at the end of the presentation. This webinar will be recorded, so if you'd like a copy, please contact me. I'll post our contact information at the end of this webinar. Today's topic, once again, is evaporative condenser air pre-cooling and RTU optimization using variable fan and compressor controls. And now let's welcome Teresa Pistacchini. Teresa, let me go ahead and get your slides. Here we go.
Hello, everyone. Thank you for joining us. I'd like to recognize Southern California Edison in sponsoring this research, particularly Jay Madden and Doreen Ahmed, who have been managing these projects on behalf of SCE. This is work that we completed in our laboratory over the past year, and these are pretty recent test results, and so I am excited to present them to you today.
Thanks.
Yeah,
okay.
Next slide. So I'm sure most of the audience is familiar with evaporative pre-cooling, but just in case, evaporative pre-cooling is using water to sensibly cool outdoor air prior to it entering the condensing unit. Dropping the temperature of the air to the condensing unit improves air conditioning cycle efficiency and, most importantly, reduces peak demand. There obviously in California is a lot of discussion concerning water use. And so I also just want to point out that we are doing research separately from what is being presented today on potentially using rainwater and gray water as water sources for evaporative cooling to lessen the potable water burden. Separately from the evaporative cooling research, we have been working on a project in fan and compressor speed control for rooftop units. If you adjust the blower speed on a rooftop unit, you can, of course, now I find a typo right here. As you reduce the fan speed of your blower, you decrease the capacity of the unit at part load conditions. Now, if on peak conditions, you can also implement pre-cooling, you can potentially control both your fan speed. You can essentially achieve this reduction at peak conditions. And it's even more important that you can control your fan speed when you have a pre-cooler present to achieve all the benefits possible. If you can also control your compressor speed, we're going to show that you can then also control your latent cooling. Now, in dry climates like California, there is a need to, what can happen in dry climates like California as you reduce your fan speed in an effort to reduce your system capacity, you can also increase your latent cooling, which is essentially unnecessary in our climate. So what this project was about looking at how you can control both your fan speed and your compressor speed to optimize your efficiency. And then we're also now considering what the potential would be if you could combine both of the technologies. So I'll go through all of our project results and so you can see what that potential is. Another one of our main objectives in testing evaporative pre-coolers was not just to test evaporative pre-coolers, but to define a test protocol that could objectively compare them in the laboratory. The laboratory is not perfect, and we can't look at everything that one could look at in the field, but we envision it as sort of a first cut where you could ensure that a pre-cooler is going to provide the performance that you need before you get out into a bunch of field installations. So our director at the WCEC, Mark Madera, is the chair of an ASHRAE Standards Project Committee, SPC 212P, which is developing an evaporative pre-cooler test protocol. We essentially developed a test protocol and then tested 5 pre-coolers on a 4-ton York rooftop unit in our environmental chamber in our laboratory as basically a way of verifying as we're essentially testing the test protocol is what we were doing. As part of participating in this project, we tested equipment from 5 manufacturers, and then we provided the results to the manufacturers as well. So this is the rooftop unit we use for all of our testing. As I mentioned, it's essentially a brand new York 4-ton rooftop unit. I don't know if there's much else to say about that. It's installed in our environmental chamber here. And we were essentially measuring capacity of the unit using, I don't have a real details or experimental planning here, but basically we're measuring airflow rate and entering and exiting temperature and humidity of the supply airflow and the unit power. So we're able to determine efficiency of the unit. We can also control our environmental conditions within 1 degree Fahrenheit on both wet bulb and dry bulb. And we run our steady state tests for a complete hour. So we have extremely controlled conditions coming into our environmental chamber and on the return air to the unit. So one of the tricks of testing evaporative pre-coolers is that it's pretty difficult to determine how much pre-cooling you're actually doing. So basically, if you look at the chart on the top right, you take your ambient air and you're going to evaporate water into it and pre-cool it to some temperature. In this plot, it shows the pre-cooled temperature is 75 degrees. The problem is it's very, very difficult to measure that temperature in the laboratory. Often there's no practical location between the pre-cooler and the condensing coil to actually measure that temperature. And also the temperature distribution may be highly variable. So it's like, where do you place your sensor? How many sensors do you need? How do you prevent them from getting wet? Because if they get wet, all you're measuring is the wet bulb temperature. And so we were essentially looking for a better way than to try and measure that temperature. Another option you can look at is the exhaust condition, because if you can measure the exhaust condition, which is much more realistic, you can essentially measure the humidity ratio and then calculate what the pre-cool condition was in order to achieve the exhaust condition that you measured. So we did use that method. We also used a novel method where we measured the COP of the baseline unit, if you look at the bottom left diagram now. So we measured the baseline performance of the condensing unit without a pre-cooler installed. Then we put on the pre-cooler, and at a certain test condition, a dry bulb and wet bulb test condition, we then measured the COP of the unit with the pre-cooler operating. And then the change in efficiency tells us what the equivalent dry bulb temperature was for that test. And now with that information, that's essentially how we get the pre-cooled condition. And then from that, we can calculate this metric known as evaporative effectiveness, which is the percentage of the distance that you pre-cooled to the wet bulb temperature. So for example, if you're up on the top right again, if your ambient condition, if your dry bulb started out at 90 and you made it all the way to the wet bulb line, which is the theoretical limit of pre-cooling, your evaporative effectiveness would be 100%. In this diagram, it looks like it's more like 60%. So that is but the approach in the bottom left corner is what is written into the pre-cooler test protocol and what we used for testing the 5 pre-coolers, the results of which I'm going to present here. So these are the evaporative effectiveness results for the 5 pre-coolers that we tested. You can see that that the 3 best performing products generally had results ranging between 50 and 80% evaporative effectiveness. And then we had 2 other products that didn't do quite as well, that in all cases were under 50% evaporative effectiveness. The error bars are basically an error propagation based on the accuracy of all the instruments that were used in this measurement, propagated throughout the equations. These are the results of the water use effectiveness, which is basically the amount of water that would be required to get the pre-cooling that was delivered if you used every last drop, divided by the actual amount of water that was used. So in all of these cases, any product that required a bleed rate, there was no bleed implemented in the laboratory. So for example, pre-coolers 3 and 4 are products that would generally have a bleed in the field. So you can see that in this case, they performed, they had the highest water use effectiveness, but we're not taking into account the bleed rate that they would require in the field, which may increase your water use, 10 to 30%. The other 3 products were once through spray products and don't require any bleed. So they had water use effectiveness on the order of 30 to 80%. One more thing to consider is that if any media is used, it's possible that you may run into situations where you are running your air conditioning cycle, but the pre-cooler is not running. So we could think of this as maybe happening at outdoor air temperatures of 75 degrees. So it's probably less of an issue for units that have economizers available. But there is something to be aware of where it's possible that you could get into that situation. So we basically just did an impact of running the unit with the pre-cooler dry at 75 degrees Fahrenheit and looked at the impact on power capacity and COP. It's two of the products, pre-coolers 2 and 5, don't have any media in the system, so really the test is not applicable. Pre-coolers 3 and 4 had very little impact from the media, and the first pre-cooler was the only one that showed any significant impact. And even so, you just have to consider whether the effect of the pre-cooling benefits at like peak conditions exceed the media penalties at these cooler temperatures. I wanted to talk a little bit about what evaporative effectiveness of, say, 60% means. This was a pretty detailed analysis, and I can't really go through all the details, but I did include a link to a previously funded SCE project that is on the ETCC website that describes this model. But basically what we did here is we looked at various Southern California climate zones, and we looked at the cooling loads in those climate zones. And we estimated the percent energy savings that could be achieved based on varying pre-cooler effectiveness. And so, if we consider that in Southern California, climate zones 9 and 10 are the most highly populated, and we consider that based on this testing, an evaporative effectiveness of like 70% is within reason, that we're looking at between 8 and 12% annual energy savings. I should also add that these results were done sort of for an average unit based on some like DEER data on how, what the performance of a typical rooftop unit is. And it's also for how a unit operates on average. So this is like if you went and replaced every unit on a rooftop, for example, this might be the realm of what you would expect to see. However, another strategy would be to install pre-coolers on the units on a rooftop that run the most. And then you'll definitely see, higher savings. Like for example, units that, bring in the ventilation air, for example. Yeah. So this is the same analysis showing the peak demand savings achievable. And as you can see, for an effectiveness of like 70%, we're in the realm of like 16 to 22, something like that. So the peak demand savings are pretty compelling. This is an example of how we're hoping to present data back to manufacturers on pre-cooler test results. The SPC protocol is going to essentially list all the information that has to be reported. So we're trying to sort of visualize that and give it back to manufacturers and sponsors and other people who may use this type of information for rebate programs and whatnot, and get some feedback on what additional information may be needed or how things should be presented. So this is just kind of a mock-up. This isn't a real test result. This is just sort of a theoretical example of what someone could get out of a laboratory test. Okay, so switching gears now, using the same exact rooftop unit that I presented previously, we installed a VFD on the scroll compressor in this 13-SEER York unit. The evaporator fan already had an ECM motor in which the fan could be varied to 5 speeds. And so we ran a whole bunch of laboratory tests where we fixed the return air condition at 8067. And then we changed the outdoor air temperature we had 75, 85, and 95 degrees. And then we varied the fan at 5 different speeds. And then we varied the VFD on the compressor to achieve 4 to 5 different speeds. Right?
Hello, everyone. Can you hear us, and can you see the screen again? Switch to the telephone.
That's right. We're halfway there.
Let me share the desktop. This is the problem. Here we go. How's that? Great. Excellent.
Okay, so there's a lot of data here. I'm just showing the test results that were measured at 95-degree Fahrenheit outdoor air temperature. On the x-axis is the varying compressor speed, and then each plot has a different y-axis. So if we look at the top left corner, you can see that, so we've plotted compressor speed versus COP, and with varying fan speed. So on the top is the key for the fan speed for all plots. But so the red is the high fan speed and the dark blue is the low fan speed. So intuitively, we can see that as we decrease the fan speed, we increase the total COP of the system. So no surprises there. And then we can also see, though, that at any particular fan speed, there is a optimal compressor speed for optimizing COP. And that increases as the fan speed increases, which also sort of makes sense because you're matching your fan and compressor, essentially. So you're sort of matching your refrigerant flow rate to your airflow rate. Now, on the top right, you can see that we've got compressor speed plotted against sensible COP, meaning the sensible cooling that is being delivered divided by the power consumption. So if we're concerned mainly about sensible cooling, you can see that the COP increases fairly dramatically as you drop the compressor speed until some point where it starts to drop. And then on the bottom left, we have some plots of sensible heat ratio, where you can see that as you decrease compressor speed, meaning you drop the mass flow of the refrigerant, you raise your evaporator temperature and you increase your sensible heat ratio. So if your main concern is sensible cooling, there are definitely some gains from reducing compressor speed. And then on the bottom right is gross capacity, which is fairly linear with compressor speed. So now taking all of this data, we can start to theorize what would happen in the field if you had control of your compressor and your fan, and you could make intelligent decisions on how to operate them. If you had a control system that could do so, and you had a pre-cooler installed. So the blue bars are power, which is essentially representative of peak demand, and the orange is COP, or cooling efficiency. So on our base, if we take our baseline unit and we add a pre-cooler, we drop our power somewhat and get a big increase in efficiency. If we take our baseline unit and we optimize the fan and compressor, I should back up and mention that all of these tests were done at this is theorizing a 95 degree day with a humidity ratio of 0.01. I don't remember what my wet bulb assumption there was, but a typical humidity ratio, typical humidity for California on a 95 degree day. So anyway, so then instead we take our baseline unit and we just optimize the fan and compressor. Well, in that particular case, we can drop our power somewhat and get a little bit of a bump in efficiency. Now we envision that we use a pre-cooler, so we drop our outdoor air temperature significantly, and then now that we have this advantage, control our fan and compressor optimally. And you can see that that's where there's some pretty promising impacts. So we can get significant power reductions and increase our efficiency. And I've plotted all this in a table on the next slide. So these are the same results in the bar chart, but plotted on a table, so you can actually see what the numbers are. But going from our baseline condition to our optimized condition, you can see that the power reduction is on the order of 37%, and the COP increase is on the order of 51%. In doing that, we're taking only a 6% reduction in capacity, which I think is pretty key. Because so essentially we can get a unit that is operating at a very similar capacity that it was before the retrofit, except that between, because the pre-cooler normally adds capacity, but then we use the optimized fan and compressor strategy to bring our capacity back to what it was, except at a much higher efficiency. And this is all happening essentially at, peak type conditions. So we hope to do more research in this area. I think the big struggle now is that the real units on rooftops are not in the lab, and we won't exactly know what the maximum efficiency is at all times, because if you go out to any particular rooftop unit in the field, it's not going to have the same performance curves that the one in our lab does. So based on all the data we've been starting to think about what possible control algorithms might look like. One of the things that we found is that the peak efficiency is very closely tied to suction pressure, which makes sense because that's relative to your evaporative temperature. Suction pressure is very easy to measure. Pressure sensors are very reliable. So we think that is potentially very useful. However, we don't expect the target suction pressure to be the same on every unit, because it's going to vary based on the equipment and the refrigerant used and all of these things. We are wondering whether the sort of optimized suction pressure could be measured at like an installation. So we're thinking about if you could, when you go out to a field to install this theoretical controller, that you could essentially do an field measurement of suction pressure versus efficiency. And however, I think we all know that it's not that easy to measure efficiency of a rooftop unit in the field. So some of the ways we're thinking about doing that is that, well, we don't care what the actual efficiency is. We're just looking for the relative efficiency. So all we need to know is basically as you cycle through different compressor speeds and get different suction pressures, we need to know how the efficiency is changing. So we're thinking about if you have, some temperature and humidity sensors, whether or not they're exactly accurate or not, you could measure a differential. And then we essentially think we can get a proxy on compressor power without actually hooking up a whole power meter. So the chart on the right shows the actual compressor power that was measured with a true power meter versus the pressure differential across the compressor times the speed, which is essentially a proxy for mass flow. And you can see that
And we're back.
gosh, we were on the last slide. We were so close. So what I was getting at on the slide on the picture on the right is that in the field we could get a measurement representative of compressor power by just looking at the pressure differential across the compressor times the compressor speed. So the idea would be to develop a control product that essentially could optimize the fan and compressor with hopefully a commercial partner, and come up with a field implementation method for that. So that is the end of the presentation. So I'll let Paul present the questions.
Excellent. Okay, everyone. Hopefully you can still hear us, and hopefully this entire webinar made it through to you and it wasn't too choppy. If you guys have any questions for us, Teresa would definitely like to answer them for you.
I think there were some up.
Let's take a look.
Up there.
Yeah. Let's see.
Oh, there was one here. Oh, from Bruce. I was gonna.
Oh, okay. Mentioned that PG&E also did the same test. Okay.
Bruce Bechet from SMUD pointed out that the PG&E lab, the work headed by Robert Davis, they also tested several of the evaporative pre-coolers that we tested and used the same protocol and got similar results. So that was encouraging to have some independent validation.
I have a question for Teresa. I think it's not necessarily something that's I don't know, concrete in terms of its answer, but where do you see this type of research going, and what do you hope to gain from doing this work?
Well, I think we've definitely identified the potential of combining the two technologies, which is significantly greater than either the technologies on their own. I think, WCEC, though, is not a manufacturer or an implementer necessarily. So we hope to, working with utility, work with a commercial partner to demonstrate
Okay, sorry about that, everyone. If you guys, so we've been having a whole heck of a lot of technical difficulties with this software. If you guys have any other questions, please go ahead and contact either me or Teresa and shoot those off to us. I will also be posting this entire webinar and the slides on our website, on WCEC's website. So hopefully this went smooth enough that the recording is okay and that the slides can help you guys as well. So I thank you. Sorry, I'm kind of cutting this off short, but I want to make sure we can get through some at least formal goodbyes before we get booted off by the internet here. So thank you. Thank you, Teresa, for joining us today. And thank you, everyone, for being here.
Oh, thank you for joining us.